Hello, my name is James Langley, and in this video I'm going to tell you about my MEng individual project titled Structured Uncertainty in the Observation Space of Variational Autoencoders. My project researches in the field of generative models, which are used to produce seemingly realistic novel data, in this case imagery. Autoencoders are one such model. The general idea is that an input is passed to a neural network encoder to produce a small code, which is then passed to the neural network decoder to try and reproduce the original input. Training takes place by minimizing the difference between the input and the output. To generate a new image, pick a random code and pass it through just the decoder. However, autoencoders do suffer from a problem. There is no constraint on what the code can be. Therefore, you have no guarantee that the code you pick to generate a new image will produce anything coherent at all. Variational autoencoders fix this problem by producing a distribution for the code to be sampled from, known as the latent space. In the same way, VAEs also predict a distribution for the output to be sampled from, which is known as the observation space. Whilst there has been lots of previous research into modifying the latent space and its distribution, in this project we are focused entirely on the observation space. That's the distribution that is predicted by the decoder and which output samples are generated from. The distribution typically used for the observation space is an unstructured Gaussian distribution with a diagonal covariance matrix. The use of this distribution introduces the flawed assumption that the uncertainty between each pixel is uncorrelated, which is not the case. Remember, VAEs reconstruct images from a compressed representation, the code, so there will be some uncertainty. However, the distribution typically used can only express that uncertainty as noise in the samples from the distribution. To get around this problem, VAEs tend to use the mean of the predicted distribution as the final output. However, this produces blurrier results, which VAEs characteristically suffer from. In my project, we remove the flawed assumption that the uncertainty between each pixel is uncorrelated by predicting a structured multivariate Gaussian distribution with a full covariance matrix for the observation space. Predicting a full covariance matrix is infeasible for all but very small images. To avoid this issue, we use a low-rank parameterisation inspired by stochastic segmentation networks, which is research authored by my co-supervisor Miguel. Some technical challenges did come up throughout this project, but ultimately it was successful and we were able to produce some great results. Let's first look at some results generated by a standard VAE. The first row is the mean of the predicted distribution. Notice the blurry results. The second row is a sample of the predicted distribution. As we expect, the uncertainty is only expressed as noise in these samples. The third row is super interesting. It is the difference between the first and the second row, that is the difference between the sample and the mean. Here it is very obvious that the samples only contribute noise over the mean. The fourth row is the variance for each pixel. Remember, a standard VAE is also capable of predicting the variance for each pixel, albeit independently. The fifth row represents a row of the covariance matrix, in particular those pixels with a positive covariance between the middle pixel and every other pixel. As expected, the standard VAE is not capable of producing a full covariance matrix, and it appears here blank. The last row is the same, but for pixels with a negative covariance to the central pixel. Comparing this to our VAE, we can see that the samples are no longer noisy and have a spatially correlated difference to the mean, which is excellent to see and shows that our method is working. Furthermore, we can now see that detailed off-diagonal elements of the covariance matrix have been populated, as we can see in the last two rows of the figure. We also trained these models on a dataset of MRI brain scans to test the feasibility of our method in a very different domain, to much success. Quantitatively evaluating generative models is very difficult due to the subjective nature of how good an image is. That being said, a current standard metric used in recent research is the fresh air inception distance, which mimics human perception. For this metric, a lower score is better. For both the human face Celeb A dataset and the brain scan UKBB dataset, our method outperforms the otherwise like-for-like standard VAE, since it can produce sharp, spatially correlated samples rather than only using the mean. Predicting a full covariance matrix does not only allow for the prediction of spatially correlated samples that outperform a standard VAE, they open up the possibility for many applications that were not previously possible. Firstly, we can now usefully interpolate in the observation space, capturing interesting information here and being able to traverse it without needing the neural network for each interpolation step. Another application is the ability to manipulate components of the generated image by regenerating the sample using a user modification to the predicted distribution. In our application, we can manipulate components for a generated image. In this example, we are able to modify hair color, background brightness, skin tone, as well as many more. Another great application we've been able to build as a result of this project is an interactive editor. We are able to update an image semantically given a small correction brushstroke. In this example, I have a black pen, and if I draw a small black brushstroke on the hair and let go of the mouse, we can see that all of the hair changes color to take effect of this correction. If I now change the pen color to a very light skin tone, and then draw a small brushstroke of this color on the face and let go, we can now see that all of the skin has got brighter to accommodate this correction, whilst also keeping effect of the previous correction as well. The hardest part of the project was overcoming challenges that arose due to local optima being found with much greater variance. This resulted in these Andy Warhol-style results, which, whilst artistic, are far from realistic. Fixing this proved to be very technically challenging. Looking forward to future work, our method is actually a modification to a standard VAE, and whilst we have not been able to produce state-of-the-art beating results, it stands within reason that our modification could also be applied to state-of-the-art methods and further improve them. Furthermore, our method could be applied in medical imaging domains, as we've seen, and this could equip medical professionals with tools for exploring uncertainties in medical images, which would be extremely beneficial, and I'd love to see this come to fruition. And that's my MEng individual project. I'd like to thank my supervisor Ben and co-supervisor Miguel for all of their help throughout the project, and thank you all for watching this video. I hope you enjoyed.